Good morning. It's my pleasure to be introducing this overview of the dark energy spectroscopic instrument. Let me start out by presenting the general context. Over the past decades, we've slowly established what is now commonly known as the standard model of cosmology. In brief, the history of the universe starts out with this hypothetical period of exponential inflation, after which the expansion continues at a slow rate. Along with the expansion, the temperature of the universe drops, such that after 380,000 years, the original plasma transitions to a universe made of neutral matter. And at that period, the photons are then free to propagate freely, giving us this first image of the universe known as the cosmic microwave background. And the matter, on the other hand, is able to start forming the cosmic web that we observed today of the large-scale structures of galaxies and clusters of galaxies. In the last 2 decades, we've realized that the expansion of the universe was actually undergoing an accelerated phase. And this was discovered thanks to the use of standard candles or type 1a supernovae, which are extremely bright stellar explosions and which allow us to study the expansion of the universe. So putting all the physics we know and the standard model of cosmology, we have a model that successfully predicts pretty much all the observations of the last 20 years. However, this model is based upon 2 main components of unknown nature: the dark matter, which is responsible for the formation of the galaxies and for the flat rotation curves that is observed around the spiral galaxies, makes up about 27% of the universe, but is of unknown nature. And even more importantly, the dark energy, this component that is responsible for the late time acceleration of the expansion, which composes roughly 70% of the universe, but is of a totally unknown nature. And understanding dark energy is the goal that DESI has been set out to achieve. So dark energy is a generic term, but what does it encompass? This accelerated expansion can be explained in various ways. It can be explained through a modification of the Einstein's field equation on the geometry side of these equations by introducing a cosmological constant lambda, which is the same trick as what Einstein used to accommodate for a steady-state universe. On the other hand, these equations relate the geometry to the energy content of the universe, and we can also explain the accelerated expansion by modifying this energy term by adding a new component, which we would describe through its equation of state, W, which relates the pressure to the density. And that's valid for all the components of the universe. Matter, for instance, has no pressure, so W equals 0. Radiation has a W of a third. And dark energy would have such an equation of state, possibly with a negative pressure term. Finally, we can also explain this accelerated expansion by looking for a more complex model of gravity. And so going beyond general relativity, and that is done by searching for hints to modifications of the laws of gravity. So the method that DESI is using to study the expansion of the universe and therefore to understand the role that dark energy is playing is by the study of Baryon acoustic oscillations, which have been shown to be an extremely promising approach. So where do these BAOs or Baryon acoustic oscillations come from? They arise from the propagation of baryon photon over density sound waves in the primordial plasma, just as in any plasma. At recombination, when the temperature of the universe has dropped sufficiently for the protons and electrons to combine and form the neutral hydrogen atoms, the plasma suddenly evolves from optically thick to optically thin, which means that the waves that propagate in this plasma suddenly stall and freeze at the location at which they've been able to propagate. So it means that around each original of the density, we're left with a ring or a sphere of excess matter that has propagated to as far as they were allowed, basically driven by the duration of this plasma, 380,000 years, and the velocity of the sound waves. So we can know very precisely that length of the radius of these sound waves, which is an imprint that is left in the distribution of the overdensity of matters in the primordial universe. And that only evolves thereafter on the expansion of the universe. And today, this imprint has a characteristic scale that we expect to be observing at 150 megaparsec. So this is illustrating this imprint that evolves from the period of the recombination when the cosmic microwave background was emitted into the distribution of matter today, given that the galaxies form where we have a larger overdensity of matter in the primordial universe and only evolves under the expansion of the universe. This is a slice of the universe as has been observed by DESI with its first year of data. And we do see that cosmic web very well with regions of overdensities and very large voids. There's no obvious sphere to be observing in this map of the distribution of the galaxies. And so the way to actually recover that imprint is statistically by studying the probability of having two galaxies separated by a given distance. And this is statistically done through the study or the measurement of the correlation function as a function of distance. And this peak here at a scale of 150 megaparsec is a clear indication that this BAO imprint is clearly visible in the distribution of matter. So this is a 3D measurement, so we can study it in various ways. We can observe it across the line of sight by measuring the angle under which we observe these characteristic scale, and that gives us access to the so-called angular diameter distance. We can also observe it along the line of sight, in which case what we measure is difference in redshift, and this gives us direct information on the Hubble expansion rate at that redshift. And so these two parameters encode the expansion history of the universe. This is looking at the BAO scale itself, but DESI does a lot more than just looking at a given scale. It measures the clustering information on all scales, and that provides us with additional information that I'm presenting here. The galaxies, in addition to being in this flow of the expansion of the universe, also have peculiar velocities, proper motions, due to their infall into the largest gravitational potentials in this cosmic web. And so the velocity that we measure, the redshift that we observe in our spectrographs with the DESI instrument, is the combination of the cosmological redshift, but also added to the peculiar redshift, the peculiar velocity of the galaxies. And so that produces a distortion in our redshift maps, which can be captured through the measurement of the Legendre polynomials shown here. And the mere existence of this quadruple term in this expansion is the imprint of these Redshift-space distortions, and so the impact of the peculiar velocities of galaxies. But this quadruple contains a lot of information on the way galaxies connect together and the galaxies form the structures. And so this full shape information actually provides information beyond what the BAO does, and in particular provides us information on the way the structures have grown and on possible tests of general relativity by studying these, the amplitude of this and shape of this quadruple expansion. So let me now introduce the DESI instrument itself. First of all, I want to thank all our sponsors and participating institutions. DESI is a very large international collaboration, roughly 900 scientists and the 72 institutions, half of them in the US and the other half from countries around the world. The way DESI works is to be aiming at building the largest 3D map of the universe ever achieved, using a sample of about 40 million galaxies and quasars, covering entirely the entire universe from the nearby universe out to about 12 billion years ago. And to do so, it uses a selection of various targets, starting from very bright galaxies and the nearby universe that can even be observed when the moon is up, given how bright they are. Then going further away, we're using pretty old luminous red galaxies. And then in the more distant universe, between redshifts of about 0.6 and 1.6, we use bright blue young galaxies that are still forming stars. And this stellar formation actually imprints the spectrum of these galaxies with a very characteristic feature that allows us to identify these galaxies and measure the redshift. And in the most distant universe, we have to use the brightest objects that are out there, which are quasars. And these are extremely luminous, and so are able to be observed in the very distant universe out to several billion light years away, but they're not very abundant. And so in the most distant universe, what we do is actually use these quasars as background lighthouses to illuminate the intergalactic medium along the line of sight. And so this is what is illustrated here. What we do is not use the quasars themselves, but the light from the quasars to study the intergalactic medium and the density of matter in this intergalactic medium. And so the way we study this intergalactic medium is through the absorption of the quasar spectrum by the intervening hydrogen along the line of sight. And you have here on the left-hand side the quasar spectrum, so the spectrum we would measure if the quasar was nearby and without having any of its light absorbed. But then in the middle panel, what you have is this absorption by neutral hydrogen at a very specific wavelength, 1216 angstrom, which is the wavelength of Lyman-alpha transition in neutral hydrogen. And what we see is that this is the same wavelength as the emission peak of the quasar spectrum itself here, but here we see it in emission for the quasar. But along the line of sight, you have this neutral hydrogen, which absorbs the lights at a lower redshift than the redshift of the quasar itself, because it's along the line of sight. And so the redshifted wavelength actually occurs on the blue side of this Lyman-alpha emission peak from the quasar. So at the end of the day, once the light from the quasar has propagated to the entire galactic medium up to the observer, what we see is leftward of this emission, Lyman-alpha emission peak from the quasar itself, a forest of absorption, which we call the Lyman-alpha forest, and which whose absorption signal is actually a proxy for the density of neutral hydrogen along the line of sight. And so this is the information that we're using to study the most distant universe for redshifts above 2 out to redshift of about 4. The DESI instrument is located on the Mayer telescope at the Kitt Peak Observatory in Arizona. It's using the original 4-meter collecting mirror that was on the original telescope, but everything else has been refurbished. In particular, we have totally refurbished the focal plane, which allows for a 7 square degree field of view, so a large field of view to collect information from many objects at a time. And then the light goes to the focal plane, located on the top here of the telescope, which is just really the achievement of this instrument. It's composed of 5,000 robotic fiber positioners, which in less than 2 minutes can position the fiber that they are holding to the exact location within a few microns of where the light from the galaxy that we want to be observing would fall in that focal plane. And so this is an animation that illustrates the motion of these fiber robots to locate themselves to the position that we want to be observing on the focal plane. And then from the focal plane, the light from the galaxies trickle down to a clean room where we have the spectrographs, where we are actually measuring the spectra of each of the objects, and therefore can measure the redshifts. So let me now turn to the results that we published roughly a year ago now. These results are based on the analysis of the first year of data from DESI, based on the analysis of close to 6 million galaxies and quasars and over 400,000 Lyman-alpha forests. So what I want to emphasize here is that just with the first year of data, DESI has already collected 2 to 3 times more spectra that it used to analyze the study of dark energy than all the prior spectroscopic studies to date, and in particular, more than 20 years of SDSS data. It was mostly located around the equatorial region, as you can see here, but we have 2 footprints, one in the North Galactic Cap and one in the South Galactic Cap. And I want to highlight that the first public release of this data will be happening in a few hours from now, and this will be presented in the special session today at 1:30 by a talk from John Mustakas. So BAO, as I said, can measure 2 things. It measures an angle, or it can measure a redshift range. And these two parameters relate to the two parameters, angular diameter distance or Hubble distance. So what we can do two things with these distances. We can combine them as an isotropic distance so as to measure the isotropic characteristic scale of the BIO feature and plot it as shown here as a function of redshift. So what we see is this isotropic distance scale as a function of redshift, and all the insets here illustrate the measurement of the BIO feature by DESI in each of the tracers that I've mentioned before, including in some cases, such as for the luminous red galaxies, in several redshift bins for each of these tracers when we have sufficient statistical power to be able to split the redshift bin in various ranges. And we even have here one bin where the luminous red galaxies and the emission line galaxy samples overlap, and which we combine into a single bin with a very nice detection at 9 sigma here of the BAL feature. So aggregated over the entire distance range or redshift range, we have a precision of 0.5%, which is already in better than all 20 years of the finalized DSS data. On the other hand, these two information separately also allow us to directly constrain two parameters, the density of matter today, and H0 RD, the product of the Hubble expansion rate today by that size of the characteristic length. And what we can see here is that all our tracers are in excellent agreement with one another. All these counters overlap extremely nicely, but it also is very interesting to see that the degeneracy angle in this two parameter space between the various tracers rotates counterclockwise with redshift, which means that by combining these various tracers, we can actually obtain a very tight, very stringent determination of these two parameters. And this is what is illustrated in black here with this tiny uncertainty ellipse. So where do we go from here? Well, first, one of the parameters of interest is the expansion rate of the universe H0. And this has gotten a lot of attention recently because of pretty strong tension between two approaches to determine this parameter. One of the approaches is to use the distance ladder approach from the light-time universe, where we determine H0 through a succession of steps, like in a ladder, where we first start out by parallax measurements to have a direct determination of the location of the galaxies, and then we use that to calibrate the next step of the ladder using pulsating stars or Cepheids, themselves used as a calibration to the next step to go to the more distant universe, where we can start using the type 1a supernovae to study the expansion rate of the universe. And this distance ladder approach gives a pretty high value of H0 of 73 kilometers per second in megaparsec. On the other hand, we can also measure H0 through a general cosmological study, such as done by the study of the cosmic microwave background by Planck. And this reaches a value of H0, which is much lower, of the order of 67.4 kilometers per second in megaparsec. So not only these two values are quite different, but if you look at the uncertainties on each of these values, you see that they're sufficiently tight that the discrepancy between the two values is actually very large, at the order of 5 sigmas. So this is quite an interesting tension in our standard model of cosmology. And so it's interesting to see what DESI can say about this story. So DESI alone only constrains the product of H0 times RD, because DESI measures angles and redshift, so dimensionless quantities. So to actually constrain H0, we need to add additional information coming from other probes. And so we can use, for instance, the study of Big Bang nuclear synthesis, which is the study of the light elements that are formed in the early universe. And so by using Big Bang nuclear synthesis, we can actually constrain the density of baryons. And because the BAO feature is related to the sound waves of the primordial acoustic waves, its characteristic scale depends on its velocity, and that velocity depends on the density of baryons. So by using Big Bang nuclear synthesis, we can actually determine that a characteristic distance RD, and therefore break the degeneracy that between these two parameters from DESI alone, and determine H0 with 1% precision. And when we plot this determination as shown here, we see that DESI is pretty close to the value that is determined from cosmic microwave background studies, and very still in very strong tension with the late time universe or the distance ladder approach from the type 1a supernovae, or the so-called shoes determination shown here. Now, the main focus of DESI is on dark energy. And so let me show where we stand regarding DESI and dark energy. Dark energy is studied through its equation of state parameter, so that relation between pressure and density. What I want to illustrate here is that this is a very difficult measurement. You have the color scale here illustrates a change in this W parameter, assuming that it is constant, by plus or minus 15% from blue to red. And you see that this plus or minus 15% change on W only impacts the parameters that we can actually measure, so the distances across or along the line of sight, by roughly 2.5%. So this is a very difficult measurement. The other information that is worth noting is that a cosmological constant lambda can actually be studied in this context also, because it would imply a constant value of this equation of state parameter W exactly equal to -1. So this is how we can check whether or not we're compatible with the cosmological constant interpretation of dark energy. Now, going back to DESI alone, here in this context where we're assuming that W is constant, we're obtaining a determination of W, which is very compatible with -1, but with only a 15% precision. However, we can tighten the constraints obtained from DESI alone by adding additional probes, such that the cosmic microwave background, which is also a measurement of the primordial acoustic oscillations in a way, because CMB does allow us to constrain the size of these features in this cosmic microwave background map. So that basically tightens the lever arm or fixes the lever arm on cosmic acoustic oscillations. And we can also use the late time universe information from type 1a supernovae, which are all at redshifts typically from 0 to 1. And so the combination of all these parameters together significantly tightens the determination of W to a precision of 2.5%, but still totally compatible with -1. That, however, is assuming that W is constant. But the power of the DESI measurements is such that you can actually start to study deviations from a possible constant equation of state. And we use this parameterization here, which allows W to vary with time. And so here we have this simple parameterization where W varies linearly with the scale factor of the universe A. A is just 1/1 plus Z. So inversely proportional to 1 plus the redshift. And so the value of W today, according to these parameterization, is W0, and WA illustrates the variation with time of this parameter. And so here, what I'm showing is the best fit determination of W0 and WA using the full combination of DESI BIO plus information from the cosmic microwave background, plus any of the 3 supernovae samples that are on the market today. We're being totally agnostic as to which one to use, but we're just plotting all 3 on the same plot here. And what is extremely interesting to notice is that a lambda CDM cosmological model would necessitate W0 equals -1 and WA equals 0. And this is several sigmas away from the best fit values that we obtain with any of these samples. And the tension ranges from 2.5 sigma to 3.9 sigma, depending on the supernova sample that we're using, but always at least 2 and almost 4 sigmas away. And this is also illustrated on the plot on the left-hand side here, where I'm again showing that same isotropic distance measurement as a function of time, or look-back time, or redshift. And in addition to the flat line curve that I showed before, which is the best fit lambda CDM model, I'm also illustrating the best fit W0 WA CDM model, so allowing this equation of state for dark energy to vary. And you do see that this is an actually better fit to the data than the flat lambda CDM model. So what does that mean for dark energy? We've seen the titles in the newspapers that dark energy might be weakening, but this is illustrated in this plot here, where I illustrate the change in the scale factor of the universe. So it's actually the change in the expansion rate. It's the expansion rate, or change in the expansion rate as a function of time, or as a function of redshift flowing to the right, which means that time flows to the left, and today is at a redshift of 0. And so the dashed red curve illustrates what we would expect in a lambda CDM model, whereas the green band illustrates the best fit model according to the W0WA parameterization. In both cases, we have that same period of deceleration of the expansion of the universe, which is due to the fact that the universe at the time is dominated by matter, and matter basically holds the universe together and decelerates its expansion, followed by this period of recent acceleration that is the origin of this study on dark energy. And this is what was discovered with type 1a supernovae back in 1998. However, what we notice in the most recent universe is that instead of continuing to accelerate as would have been predicted with a lambda CDM model, we instead see a slowdown of this expansion and a possible turnover. This is yet to be determined. But this clearly shows that the acceleration of the expansion is slowing down. And if that is the case, it is an indication that dark energy is not as strong as what would have been needed according to a lambda CDM model, and therefore might be weakening in the recent epochs. We also mentioned that this could be due to modification of the laws of gravity, and that we had to be looking for possible extensions of general relativity. So this slide looks complicated, but I'll just walk through the main points. This possible explanation of accelerated expansion can be studied through the Poisson equations that govern the trajectories of particles in gravitational potentials. And so we have one such equation for massive particles and one for massless particle or light. In GR, these two gravitational fields are identical, and we have no need for these additional parameters mu or sigma, which are both equal to 0. But if we want to allow for modified gravity, then we do allow for these two potentials to be different. And we also introduce these two parameters here, mu and sigma, which relate to the dark energy density and are parameterized today by the values mu naught and sigma naught, which would be the value of these two parameters today. DESI studies the clustering of galaxies, and so is only sensitive to the equation that relates to massive particles. And so what DESI can constrain is the determination of mu naught. To constrain sigma naught, on the other hand, you need a study that is sensitive to the trajectory of light or of photons. And this can be done in particular through the study of cosmic microwave background at late times, for instance, via the gravitational lensing of the CMB. What we see in this plot is that indeed the constraints obtained by DESI in green are only constraining mu naught, no sensitivity to sigma naught. But what is important to see is that they're totally compatible with mu naught equals 0. And combining with CMB, we obtained red or blue contours here, depending on the actual likelihood that we're using from the CMB. But in both cases, you see that the 0, 0 value is totally compatible with what we're obtaining. And so DESI sees at present time no hint for any deviation compared to general relativity. And finally, just one word on neutrino masses. DESI can also study the impact of neutrinos on the expansion rate of the universe. And this is illustrated here. The sum of the neutrino mass as a function of h naught. In CMB, there's a strong degeneracy between these two parameters that DESI can actually break by determining h naught, as we've seen in the early slides of this talk. And because the value of h naught constrained by DESI is pretty high compared to what CMB would prefer, this puts a pretty tight upper bound on the sum of the neutrino masses. to 0.08 electron volts using DESI and CMB. And we can also even tighten this information using the full clustering information down to 0.07 electron volts with adding the information on all scales. However, that's in a lambda CDM model, and we've seen that DESI prefers varying dark energy model described by Delano WA. And in that case, the sum of the neutrino masses is significantly relaxed to an upper bound of 0.175 electron volts. And interestingly, also, this is illustrated on this plot here, we see that while the best fit value of the neutrino masses is actually in the negative values for a lambda CDM model, this moves back into the positive range once we allow for an extended model of the background expansion of the universe. And so this is all that I wanted to show today. DESI was just its first year of data, has obtained really tantalizing hits for modified dark energy model and going away from lambda CDM. And this is an illustration of what was actually shown on the front page of the New York Times when the results were published, and which is a fly through of the actual 3D map that has been measured by DESI with the actual location of the galaxies. But the year one results are statistics limited. And so I strongly encourage you to attend the special session today, the same as the one I've mentioned before at 1:30, where we will show the results that we obtained with 3 years of BAO data. And these are some of this data illustrated here. Thank you.